Alrighty, physics, we are diving into chapter 9 today, work, power, and energy. And we're looking at the relationship of these three ideas, work and power and energy. Work and energy are very, very closely related. You're going to actually see the same units and a lot of the same formulas there. Power stands out a little bit because time matters in that particular measurement. So we are looking at chapter 9 today. First, work. Work is the energy required to move or change the state of a system. So if you pick up a box and you move it somewhere else and you set it down, the force that you expended to move the box times the distance that you moved the box is going to give you the work that you did. So force and distance are the two things that matter there. We also have this trigonometry term, the cosine theta there, because we need to correct for the idea that you may be pushing not in the direction of displacement. So it's the force in line with displacement times the distance of displacement times how far you moved it, which matters. So the formula there, W equals force times distance times cosine of theta, okay? And the unit that we measure is the Newton meter. Newtons for force, meter for distance or displacement. And Newton meters has a derived unit, and that is the joule. So a Newton meter is a joule. So we'll be labeling these things in terms of joules. Here's an example of the equation given to you in a graphic form. If you have an object here and you push on it at this angle, even though you're pushing on it in this angle, if it moves like this, right, you've pushed on it and you've done work because you've exerted a force over a displacement. And so we need to correct for the fact that the displacement and the direction are not the same, so that's the cosine theta term there. You can also see that example here with wind and sailboats. Even though the wind is coming this direction, depending on how they turn the sail, they can make the sailboat go in lots of different directions with the same wind, okay? So the force and the displacement are not necessarily in the same direction. That's why we have to have the cosine of theta there to correct for that, okay? Here's a little equation we can do some math with. If little Joey pushes with a force of 18.3 newtons on the handles of his mower, which make an 38-degree angle with the ground, moving the lawnmower for 5 meters, how much work has he done? Go, Joey, go, mow that lawn. Okay. 18.3 newtons of force going down the handle, and 5 meters of distance. 5 meters of distance, but Joey is not pushing parallel to the ground. He's pushing on the handles at an angle. So we've got to correct that, cosine of 38 degrees, okay? Cosine of 38 is 0.78801, and then we just multiply straight across and we get 72.1 and change, correcting for significant digits, 72 joules. So Joey pushing on those handles and moving that lawnmower for 5 meters has done 72 joules worth of work, okay? Pause the video, go back and look at that again. If you have any questions, go ahead and post them in the question section of the blog page, okay? Alrighty, work, power, and energy. Now we're looking at work in springs, okay? Springs exert a force that resists both compression and extension from their position of equilibrium. So if you have a spring, its natural length when nobody's messing with it, that length is the position of equilibrium. And so a spring likes to stay at that point. It will resist being stretched or being squished. And the amount of resistance is a term called K, the spring constant. And that force is a function of, the force that resists it is a function of that spring constant and how far you have displaced the spring, right? And so the force of the spring is its constant times its distance. And the amount of work that a spring can do is 1/2 times the spring constant times the displacement squared. So if you compress a spring a certain amount of distance given its constant, it can then do work for you, or it will push with a certain force. And both of those are easily calculated, okay? Work can be done from the outside on the spring. You can do work to compress the spring, or the spring can do work on an outside object, and I'll show you a picture of that in just a moment. And so these two equations together are referred to as Hooke's law. It's the same Robert Hooke that first named the cell a cell. He did all kinds of things. So Hooke's law has two forms. It's these two equations. All right, let's look at some pictures. If this spring would like to be this size, but you put a certain weight on it, you can do work on the spring because of the weight, the force here of gravity on the weight, and you can stretch that spring. You can put more weight on, greater force, and stretch the spring more, okay? Or you could ask a spring to compress and lift up an object. Like if you pulled out a spring, put a weight on it, it might be able to pull the weight back up. So the spring can do work on the weight, or the weights can do work on the spring. Depends on how you want to look at it. Here's some pictures of that. Here we have an object with a certain mass compressing, or at rest, sorry, at equilibrium. Then you can stretch it out and do work on the spring, and so the force is messing with the spring down here, right? The spring is wanting to pull that mass back. Or you can push on the spring and compress it, and the force of the spring is wanting to push the mass out. So whichever way you mess with the spring, it has a force that wants to go back to equilibrium, go back to rest. And here's an example of doing work with a spring. So if you compress the spring with this little plastic ball shooting gun, you compress the spring, you did work on the spring. And then you push your plastic ball in and you pull the trigger, and the spring is released. It does work on the ball. So either you can do work on the spring, or the spring can do work on the ball. Okay, let's do a little math with that. So this big nasty truck has a mass of 1,532 kilograms, probably a lot more than that, but that works for our example here. Each of the four springs, each of the four shock absorbers here is 0.8 meters long, nearly a meter long. In order to support the truck, what is the minimum spring constant each spring must have to hold it up? So the force of the spring is its, the force of weight, not the spring, the weight of the truck is its mass times gravity. Let's get that first. So 1,532 kilograms times the acceleration of gravity. The truck is pushing down with a total force of 15,028 and change Newton. So each shock absorber has to support a quarter of the mass of the truck, or of the force of the weight of the truck. So we have the weight of the truck in newtons divided by 4. Each shock absorber has to be able to hold that much weight. All right. So if each spring is 0.8 meters long, then Hooke's law force will give us the minimum constant for a spring fully compressed to support this weight. And so the spring has to hold a certain amount of weight. It's got to have a certain force. I know the distance. I don't know the spring constant right there. That's what I'm solving for. So I'm going to rearrange my formula so that it's K equals F over D. And then I'll be able to plug in what I know. Here I have the newtons of the weight of the truck and the distance that the spring is compressed. And these things have to balance out to a certain spring constant. I just do the division, correct for significant digits. And my spring constant has to be 4,700. That's a ridiculously stiff spring, but that is the kind of thing that you find in the suspension of a truck. All right, so there you go. A couple more examples here for you. Power now. Power is the rate at which work is done. So you do work, good for you. How fast do you do it? If you do a certain amount of work slowly, well, you don't exert much power. If you do the same amount of work quickly, you exert more power. You can see that with regard to engine analogies. If I just need to get from point A to point B, and I can take all day to do it, then I can have a very low power engine. But if I need to get from point A to point B in 5 minutes, maybe I need to have more power from my engine to move my car over there. Okay? Power has to do with the speed at which work is done. So the mother equation for that is power is work divided by a certain amount of time. Okay? You could also blow up the work equation and isolate the mass from that and the unit time, and you could turn that into a velocity. And so you could look at that as power is the force applied along the displacement, so that's the cosine theta, at a particular velocity, or to achieve a particular velocity. And so you could also have this equation. These two are essentially synonyms. They mean the same thing. Use whichever one is more convenient for the circumstances you've been given. Okay? We measure power in watts. light bulbs, motors, appliances measured in watts because of the power that they can produce, the power that they use. And so 1 watt is 1 joule per second, doing 1 joule worth of work every second. That's a watt. So a 60-watt light bulb consumes 1 joule of energy per second times 60, so 60 joules of energy per second. Okay, so that's just a quick little picture there of power. Let's look at an example. If carrying a board from a truck into a hard goods store and stacking it on the shelf represents 32 joules of work, let's just say it does. Okay, and Billy, the employee, took 45 seconds to lap each board. So he's going 45 seconds out to the truck, back to the shelf, out to the truck, back to the shelf. How much power would he expend if he carried 60 boards one at a time? And you'll see something here. If you're doing the same amount of power in multiple repetitions, each repetition will serve as an example of power. So let's look at that. Power is watts divided by unit time. Carrying 1 board is 32 joules. Sorry, work divided by unit time, not watts. Carrying 1 board is 32 joules. He's going to do that 60 times. Each lap takes him 45 seconds. He's going to do that 60 times. Well, 60 in the numerator and 60 in the denominator cancel each other out. So if you have multiple repetitions of the same thing, you can just look at 1 repetition. So that's essentially just 32 joules in 45 seconds. And that's 0.7111 watts, or you can correct for significant digits with 2 significant digits, 0.71 watts. That's a pretty dumb bulb. Billy is not putting out very much effort, not doing very much power, right? Not using very much power. But he's stacking those shelves, man, at his 0.71 watts. Not very impressive. But then along comes his boss. Billy's boss gets tired of seeing Billy carry 1 board at a time and uses the forklift to move the entire stack in 1 minute. Ah, much better. That's why he's the boss. How much power did that take? Well, he's also moving 60 boards that each represent 32 joules worth of work. But he's doing that in 60 seconds. Okay? So 60 times 32 divided by 60, if you do that math, is 32 joules because there's 60 here, 60 here. That's happy for us. They cancel each other out. 32 joules in 1 second, 32 watts. He's doing 32 watts of power. Remember, dim bulb was doing 0.71 watts worth of power. This does 32 watts of power, same work, less time, more power. Okay? Alrighty, we're getting there. Kinetic energy. Kinetic energy is the energy of motion. So there is something called the work energy theorem that says that the total work done on a system by all the external forces acting on it is equal to the change in the system's kinetic energy. So the amount of change in kinetic energy is one way to look at work, and you'll see how that comes into effect in a little bit here. We measure kinetic energy in joules, just like we measured energy in joules or work in joules. They're the same unit, okay? So kinetic energy is 1/2 times the mass of an object moving at the square of this velocity, or times the square of its velocity. That will give you the kinetic energy of that system, okay? So the bigger something is and the faster that it's moving, the more kinetic energy that it has. Let's look and see how that plays out. Let's say you were wanting to buy a gun to defend your home, and you live in a neighborhood where there's been break-ins and you don't know how quickly the police will get there. So you say, okay, I'm going to buy a firearm and defend my family. Should I need to? What should I buy? Well, the 2 contenders out there that claim to be the best stopping power ammunition are the .45 and the .357. And you want to know which one really packs the biggest wallop and stops the biggest intruder who may be high on drugs or something like that. So you need the most kinetic energy in the round possible. So here we go. The atomic brand .45 caliber ACP plus P round, there it is, has a projectile mass of 12 grams. So the bullet weighs 12 grams. An initial muzzle velocity of 300 meters per second. So it leaves the barrel of the gun at 300 meters per second. Same ammunition company has a .357 that weighs less, 10.2 grams, less mass, but faster muzzle velocity, leaves the barrel of the gun at 411 meters per second. Which one has more kinetic energy? Kinetic energy is 1/2 times the mass times the square of the velocity. So for the .45, 1/2 times the mass times the square of the velocity. Square first, that's 90,000. multiply that by the mass. We've got to be in kilograms here, which is why 12 grams became 0.12 kilograms. Just do the simple multiplication across, and the 45 caliber round has 540 joules of energy. It's a lot of energy. Compare that to the 357. Which one is more? The kinetic energy of the 357, 1/2 times the mass times the square of the velocity. Less mass, traveling faster. Square that number, multiply across, correct for significant digits, 861 joules. So even though the 357 is a smaller round, it carries more kinetic energy, and that would be the gun that you would want to have to defend your family. There you go, little home defense technique tips along with your physics there. That's for free. Okay, potential energy. Next one we want to look at. Potential energy is the energy of position. It's a stored energy, and it could have its position because it could fall from there, in which case potential energy is the mass times the force of gravity times the height above which it could fall. Or it could have potential energy because it's affected by a gravitational field. That gets a little bit more complicated. Look in your book for some examples of this one. We will do very little with this in class. The potential energy here of a gravitational field looks just like the equation for gravity, but that turns into potential energy in joules. Okay, and then you could have potential energy because of an elastic force. You've pulled on a spring and you've locked the spring open, and the spring would like to pull that shut. And so the potential energy of a spring is very much like the equation for the work that a spring can do, because it's the same concept, right? And so all of these are measured in joules. Joules is the unit for work and for energy. Okay? Now, let's look at an example here. Let's say you have a bowling ball on top of an observation deck that is 5 meters above the roof of a building, which is 5 meters above the ground, and there's an open manhole with a 5-meter pit. So this bowling ball is a total of 30 meters above the bottom of this pit. If you were to push it and it hit here and then rolled and then did a bullseye shot into the hole, how much potential energy did you release? What is the potential energy up here? Well, it's mass times gravity times the height, mass times gravity times the height. We just want to add that together. And so you just multiply across, and there are 1,000 joules, when you correct for significant digits, of energy up here represented by this bowling ball. Okay? Alrighty. Kinetic energy is very much related to potential energy. They come together in a term called mechanical energy. But before we can get to that, we need to talk about conservative and non-conservative forces. So conservative forces exchange all energy between them without losing anything. So potential energy turning into kinetic energy and back, okay? This relationship conserves energy. Something either has potential or part of it has become kinetic, or part of it has gone back to potential. Show you some examples there. Non-conservative situations lose some energy to other sources that cannot feed the energy back into the system, so it becomes mechanically unuseful. Things of that nature would be friction, heat, light, noise, things where the energy leaves the system and doesn't come back. There are two tests to see, is this conservative energy? You could say, is the pathway of the work that you've done independent of the result? And if so, then the conservative forces exist. Or if the object starts and ends in the same point, then it is conservative. If neither of these are true, it's non-conservative. So let's look at some examples here. When I throw this boomerang, or when this young lady throws this boomerang, it's going to leave her hand, and if she throws it right, go out and around and come back. So it started and ended in the same place. It currently has potential energy that will be transferred into kinetic energy and restored to potential energy. And so that is a complete circuit that's conservative. This skier currently has kinetic energy. If he goes up a hill, he will lose his speed, but he will have transferred some of that kinetic energy into potential energy, because now he's up here. He could ski back down. Okay, so that's conservative. Or if you look at an object and the result doesn't matter for how you get from A to B, then it's conservative energy. If none of these kinds of situations are true, then you have lost some energy somewhere, and that's non-conservative. Okay, last one is mechanical energy. So mechanical energy is the sum of the work that is being done through kinetic and through potential energy. So we use the letter E for mechanical energy, and it represents the sum of the kinetic and the potential energy, along with any non-conserved forces. A lot of times in high school level physics and in non-calculus based physics, we will tell you to ignore non-conserved forces. So most of the time, you'll just be looking at the potential and kinetic energies and saying that the sum of those represents the total mechanical energy in a system. And so you could set the potential and mechanical energies at one point in time equal to the mechanical potential energies at a different point in time, and use the two equations to solve each other. So let me show you just a quick example of how you can do that. If you have a dude skateboarding along, okay, and he weighs a certain mass and he has a certain velocity, then you could calculate his kinetic energy. His potential energy right now is 0 because he's down at the ground level. And the sum of 0 and his kinetic energy will give you the mechanical energy. All right? And then at the top of the ramp, he has all of his energy turned into potential energy, no kinetic energy. He has stopped. His velocity up here is 0. So up here, all of his energy is potential, 0 kinetic, and potential plus kinetic equals the mechanical. The mechanical here and the mechanical here are the same. And then you could look at some moment in between. When his height is 1 meter, you could calculate the potential energy there based on his mass and his height. And then you could solve for the kinetic energy at that point. And you could use that to calculate for the velocity. Go ahead and pause the video at this point and try to answer this question on your own, and we'll go over it when we see each other tomorrow in class. God bless you guys. If you have any questions, put them in the comments field of the blog, and I'll see you tomorrow.